The Leidenfrost effect is when a liquid like water floats on its own vapor instead of touching a very hot surface. Let's understand this with a common example that happens with everyone in the kitchen. Imagine you're cooking and accidentally spill a few drops of water onto a very hot pan. Instead of the water immediately sizzling away, you notice something unusual but really cool. The water droplets seem to float and glide across the pan's surface like tiny hovercrafts, lasting much longer than you'd expect. This awesome-looking phenomenon is the Leidenfrost effect in action, named after Johann Gottlob Leidenfrost, the German scientist who first described it in 1756. So, why does this happen? The secret lies in what occurs at the exact moment the droplet meets the scorching surface. For water, the Leidenfrost effect typically begins on surfaces above roughly 193 degrees Celsius or 380 degrees Fahrenheit, a threshold known as the Leidenfrost point. When a droplet hits a surface this hot, the bottom layer of the droplet instantly vaporizes, turning into steam. Normally, on a cooler hot surface, this steam would bubble away. But on a super hot surface, something different happens. Instead of the droplet boiling away instantly, the bottom layer of the liquid vaporizes so rapidly that it creates a cushion of steam between the droplet and the hot surface. This vapor barrier acts like a protective shield, insulating the remaining liquid from direct contact with the heat source. The droplet essentially rides on its own steam, which explains why it can glide around so effortlessly and survive much longer than expected. The key to understanding why this happens lies in the fundamental principles of heat transfer, which govern how thermal energy moves from one object to another. In physics, there are three main ways heat can transfer: conduction, convection, and radiation. When we examine the Leidenfrost effect, we're primarily dealing with the dramatic difference between conductive and convective heat transfer. Normally, when liquid touches a hot surface, heat transfers efficiently through direct contact, a process called conduction. This direct contact allows for maximum heat transfer efficiency, which is why water normally disappears almost instantly when it hits a hot surface. However, in the Leidenfrost effect, the vapor layer that forms between the droplet and the surface acts as a thermal insulator, fundamentally altering how heat moves from the surface to the liquid. This vapor layer is a poor conductor of heat compared to direct contact, creating what engineers call thermal resistance. To understand this concept, imagine trying to warm your hands by holding them near a campfire versus touching a warm rock directly. The air between your hands and the fire, like the vapor layer, transfers heat much less efficiently than direct contact with the warm rock. This means heat transfer becomes much less efficient in the Leidenfrost state, paradoxically protecting the droplet from the intense temperature. The thickness of this protective vapor layer is typically only a fraction of a millimeter, but this tiny distance makes an enormous difference in heat transfer efficiency. The Leidenfrost effect has numerous practical applications and examples in our daily lives. Blacksmiths have unknowingly used this principle for centuries when they test the temperature of their forge by sprinkling water on hot metal. If the water dances and glides, they know the metal is hot enough for their work. In modern cooking, chefs use this effect to test if their pans are properly heated for certain cooking techniques. When water droplets bead up and roll around the pan instead of immediately evaporating, the pan has reached the ideal temperature for searing. In steel manufacturing, they use water to cool down hot steel as it's being made. The Leidenfrost temperature for this process is usually between 700 to 900 degrees Celsius. That's extremely hot, about 1,300 to 1,650 degrees Fahrenheit. If engineers don't understand this effect properly, they might accidentally cool the steel too quickly once it drops below the Leidenfrost temperature. It's like the difference between gently cooling a cake versus shocking it with cold air. Sudden temperature changes can cause problems. The phenomenon also appears in more dramatic scenarios. When molten lava flows into the ocean, the Leidenfrost effect can cause seawater to form protective vapor layers, creating spectacular steam explosions and unique geological formations. The Leidenfrost effect reminds us that sometimes in science, as in life, a little distance and the right conditions can help us survive even the hottest situations.